Hi, in this video I will give a short description of assignment 4 and discuss a little bit about each of the exercises that you're supposed to deliver. So assignment 4 is about unsupervised learning, which is the subject of lectures 11 and 12, more specifically clustering and dimensionality reduction. So you have 3 exercises here, and it involves implementing 2 unsupervised learning methods, one clustering and one dimensionality reduction. And they're not the ones that we saw in the lectures. They're a little bit different, but I hope not so much that you can still get around to implementing it. Then you will test them with data sets of your choice. I'll talk a little bit more about that. But the most important part here is that you should deliver the results in a Jupyter notebook. So the first 2 exercises are basically code. You will implement a function that will perform the process of either clustering or dimensionality reduction. I'm giving a definition specifically of what the function should be called and what kind of parameters it has, the returning values, and so on. So they should be in the notebook in their own cell. And the notebook should then combine these codes with text and images in order to answer all of the requirements of exercise number 3. So exercise number 1 is code, number 2 is code, and then number 3 is more like a visual report where you have text and images, and you will use the things that you implemented in the first 2 exercises, okay? So let's start with the first one, exercise number 1, clustering. The goal is to implement the clustering algorithm called bisecting k-means. This is a little bit of a mix between hierarchical clustering and k-means. So it's a mix of the 2 of the techniques that we saw during the lecture. You know, here you can see the steps of implementing this. I'm not going to go over that in details. I'll let you guys read that. And if you have any questions, of course, you can come to me and the teaching assistants. It's all described here in details, I hope. But the most important part here is that this should be implemented in a function, right? So I'm actually defining it over here, implement the bisecting k-means algorithm in a function called bk-means. So this is what the function should be called. Please stick to it. Then I'm describing here what's the input and what's the output. So if I call this function, I will give an input, then you apply the clustering, and then you generate as output something as is being described here. Okay, so basically that's it. That's just implementing this function. And then, of course, I will test if the function does what it should do. So if the results are, you know, coherent with what is expected. Of course, I will also look at the code, and every code, I mean, it does not necessarily do the exact same thing. Hopefully ideally everyone will have the same results, but that's not how it works. And it's okay as long as the results are coherent and it makes sense with what is expected. Oh yeah, you didn't. This bisecting k-means, you use the k-means algorithm as part of the process, so you do not need to re-implement k-means, okay? Or else that would be too much. So you can reuse k-means from other implementations, like from scikit-learn, for example. So you just have to reuse it and then include it in the overall process of the bisecting k-means algorithm. Then exercise number 2, again, code. Again, the implementation of one function. And in this case, it's nonlinear dimensionality reduction. And basically, it's the implementing something called the Salmon mapping, which is one of the classic standard nonlinear dimensionality reduction. Actually, maybe the first one. It's a very old, actually, algorithm, but it's still used, and it's still very interesting, especially when it comes to implementing, you know, this optimization process that is so common with dimensionality reduction, right? And again, the steps of the algorithm are described over here. I hope they are in enough details that you can re-implement. You should refer to some slides of the lecture. Actually, I'm pointing it out here, like, for example, see slide 47 of lecture 12, or see slide 48 of lecture 12, where the formulas are actually detailed, and then you can just implement them here, right? And it's using gradient descent. So I guess I know you have experience with that from the previous lectures and the previous assignments. So I hope it's not too much also. So again, implemented in a function. In this case, the function should be called salmon. I'm giving here a description of what's the input. So what will I like send as an input to the function? So what the function should expect as an input, the data, the parameters, and so on. And then it should generate as output another vector here. In this case, n by 2, because it's a two-dimensional projection, right? And one note here that's very important is be careful with division by 0 when computing the gradient descent. This happens a lot, and that's because when you see the formula, you see that there's a denominator in one of the computations that can become very small. And if the denominator is really, really, really small, almost 0, then the gradient will basically become very, very large, because when you divide something by a very small value, the result is a very large thing, right? So you could see some weird results with the gradient descent if you let it go as without checking. So my advice is to treat this by limiting how small the denominator can be. So you can have a small constant that you say, well, these denominators should never be smaller than this constant or something like that. And also the same notes from exercise 1 also applies here. So all the stuff like use Python and so on and so forth. And then finally we get to exercise number 3, where the idea is that you're going to take the stuff that you implemented in 1 and 2, and then you're going to build a report where you're going to visualize some results and discuss them a little bit. What are the strengths of the stuff that you implemented? So first of all, you will have to choose 3 data sets. It's up to you. Okay, I want creativity. I want you guys to be creative. I don't want you to just, please do not play safe. Please do not use data sets that you can find everywhere. Please be creative and find some interesting data sets with interesting results, because that's what I expect of you, and that's what you will be expected as machine learning engineers, that you should be able to go out there and look for interesting problems and come up with interesting solutions and discuss them. So it's not just about code, it's about also discussing what's happening. So I gave some examples here of places where you can get new data sets. So just go there, find 3 interesting data sets. I will not be there are not any big restrictions as to which data sets you should take. So the only thing is that it has to have more than 4 features. And you cannot use the iris dataset, because the iris dataset has 4 features anyway, so that wouldn't work, because you need more than 4 features, so you need at least 5. And also it needs to be something where you have labels for that. And the reason why we want labels here is not because they're part of the algorithm, but simply because that's how we will validate the results. Okay. And then some sources here where you can get some data sets, and also try not to get anything too big. Obviously the more data the better, right, in the real world, but here depending on how you implement it, it may become very slow. So I would recommend something around 1,000, maybe a couple of thousand observations, because this is just a little exercise, right? It's not supposed to be this super effective, efficient implementation and so on. So if you get too much data, then it becomes a little bit slow, and then that's frustrating even for you when you're testing your implementation. So let's try to keep around maybe 1,000 or a couple thousand observations. So something around like 1,000 by 5 or by a few more features. That's enough for this exercise. Then the first thing you're going to do is you're going to compare some DR techniques, right? So you're going to compare your implementation of salmon mapping with PCA and t-SNE. So you can find PCA and t-SNE in scikit-learn, for example, or in any other Python implementations. There are thousands around. So you're gonna run salmon mapping, you're gonna run PCA, you're gonna run t-SNE for each data set. So you have 3 techniques and 3 data sets. And when you combine all against all, then you have 9 results, right? Every technique with every data set. So that becomes 9. Then you're going to build a scatter plot matrix, as we call. So that's a matrix. There's a 3 by 3 matrix, and each cell of this matrix is one scatter plot. And then the DR techniques will be the columns. So let's say the first column is SAML mapping, the second column is PCA, the third column is t-SNE, and each row is one data set. So the first one, well, whatever data set that you choose in the first row, in the second row, and the third row. And then that gives you a complete overview of the results of all the 3 techniques with all the 3 data sets. And then you color the points by their target variables. So since I'd said here that they must have labels, then you just assign a color to each label and then color the points by that, so that when we look at the scatter plot, we can have immediately an idea of how the classes are separated in the results, right? So you can have an estimation, like a visual estimation of how good is the class separation. Then you do the scatter plot matrix, you show it, this visualization, and then I want you to answer these 2 questions very shortly, like 1 or 2 paragraphs most. Don't worry too much about details. It's more about how do you see the results that you got, and how do you feel about them? What do you think about them? So in your opinion, which technique performed the best for each data set regarding the separation of classes? So look at each data set and say, okay, in this one, t-SNE worked better, and in that one, PCA worked better. And talk a little bit about why you think, why is that so? Like, what are you seeing that led you to believe that? And then how are the classes in the data sets separated? Are some classes or data sets easier to separate than others? So this is interesting because this gives you a very interesting insight on the structures that are present in the data set, and even in how hard it is to separate the classes on that data set, because this could even translate in good or bad classifiers later. So, I mean, just estimation, right? It's not a statistical evidence or anything like that. It's just a visual estimation of, which data set. I just want you to reflect on which of these data sets that you chose are easier or harder to separate the classes and everything. Then comparison of clustering techniques. Now, in this case, you're going to choose one of the DR techniques from the previous exercise. Could be yours, could be PCA, could be t-SNE, whatever one that you feel works best, or you feel that's more interesting. Then you're gonna apply that. Well, you already have that for each of the data sets, right? Because you've already generated that, so you can just reuse the layouts that you already have. And then you're gonna apply 3 different clustering techniques in these data sets, okay? So again, the resulting visualization is again a 3 by 3 matrix where each cell is a scatter plot. So it's still a scatter plot matrix with 9 cells because you have 9 results. And in this case, every cell is a scatter plot of the chosen DR technique applies to each data set. So in the rows. So again, you have data set 1 in first row, data set 2 in the second row, and data set 3 in the third row. But in this case, the entire row, let's say the 3 cells that compose the row are the same because you have chosen one DR technique now, okay? So it's the same DR technique with the same data set in the first row, the same DR technique with the same data set in the second row, the same DR technique with the same data set in the third row. So the rows are different, but in this case, the columns are the same. And then what you're gonna do is you're gonna color the points showing the results of each clustering method in the columns. So in the same way that you did with the classes in the previous one, while here in 3.1, you colored the points by their classes, their labels. In this case, you're gonna apply some clustering, and then you're gonna color the points by the cluster that were assigned to them, okay? Instead of the classes. And then again, I want you so then you're gonna look at it, and each column is gonna be a clustering. So for example, the first one is bisecting k-means, the second one is just classic k-means, and the third one is hierarchical clustering for each data set. So bisecting k-means for each data set, classic k-means for each data set, then hierarchical clustering for each data set, right? So then again, you're gonna look at this, and I want you to tell me, in your opinion, which clustering technique performed the best for each data set, and why do you think that? So in this case, you're not analyzing the DR anymore. You're not analyzing the actual scatter plot because you already did that in the first one. Now you're analyzing the actual clustering. So the results of the clustering, okay, which are expressed in colors. So this is the goal of the final technique. And then a couple of references here for the implementations that you're going to do, okay? So I hope this was clear. I hope, well, anyway, obviously there will be questions, and please just let us know through Slack or Moodle if you have any questions, and we are going to try to help you as much as we can. Okay? Good luck.